Hi class, in 13.5 our learning targets will be calculating the area of rhombi and kites. We will also be using formulas to compute the area of rhombi and kites, and then much like we have with the other lessons in chapter 13, calculating the area of composite figures. If you take a look at page 876, let's start off with the area of a rhombus in problem number 1. Please have your cheat sheet handy that I gave to you so that you can help understand, it helps you understand the difference between the characteristics in all of these quadrilaterals that we've talked about in chapter 13. Problem number 1 says, recall that a rhombus is a quadrilateral with all sides congruent. It says, Mr. Graham asked his math students to sketch a parallelogram. These are two of his students' sketches. So what I would like you to do to get started is answer questions 1, 2, and 3 with your group members. Go ahead. Number 1 asks us, how are the two sketches similar? Both of the sketches are parallelograms. Number 2, how are the two sketches different? If you look at Molly's sketch, it is a parallelogram with opposite sides that are congruent. James, his sketch, is a parallelogram with all sides that are congruent. Number 3 then says, Mr. Graham told his class that both sketches are examples of parallelograms, but James's sketch is an example of a special parallelogram. Why would James's sketch be considered special? Because all 4 of the sides are congruent in that quadrilateral. Molly's sketch does not have all 4 sides that are congruent. Take a look at the top of page 877 and answer number 4, 5, 6, and 7 again with your group members. I think that if you refer again to the cheat sheet that I gave you with the characteristics of different quadrilaterals, it should be pretty easy to answer these questions. Go ahead and do that with your group members. If you take a look at 4 through 7 on page 877, number 4 first, only the second statement would be true. All rhombi are parallelograms because if 4 sides of the quadrilateral are congruent, then opposite sides will always be congruent. It is possible to draw a parallelogram that is not a rhombus, but it is not possible to draw a rhombus that is not a parallelogram. Again, if you refer back to your cheat sheet and follow those arrows, I think that should have been easy to understand. Number 5 is just a sketch that I came up with of a parallelogram that is not a rhombus. You can see that my lengths of my sides, my opposite sides, are not congruent. That's what makes it a parallelogram. Number 6 is not possible. I can't sketch a rhombus that is not a parallelogram. And finally, number 7, it says Molly concluded that all squares must be rhombi and parallelograms. Yes, she is correct. Again, if you refer to that cheat sheet and follow the arrows, a square is a quadrilateral with all sides congruent and all angles congruent, so all squares are also considered rhombi and parallelograms. Let's go ahead and on page 878 we're going to skip number 8. Let's take a look at number 9. It says, since all rhombi are also parallelograms, what formula can be used to calculate the area of a rhombus? Use B for the length of the base, H for the height, and A for the area. The area of a parallelogram formula can be used then to calculate the area of a rhombus. We should already know that the formula for finding the area of a parallelogram is A equals B times H. So again, building off of our prior knowledge of geometric figures that we've already talked about in chapter 13. Alright, let's move on to problem number 2 on the bottom of page 878. Now let's talk about the area of a kite. Again, Carnegie is understanding that you already know what the characteristics of a kite are. It says, recall that a kite is a quadrilateral with 2 pairs of consecutive congruent sides with opposite sides that are not congruent. Just to get a good understanding of what the definition of a kite means, if we take a look at kite ABCD, here would be 1 pair of consecutive congruent sides. AB and AD, they share common endpoint A, and then BC and CD is the other pair of consecutive congruent sides. They share common endpoint C. Let's take a look at page 879. Number 1 says, Mr. Graham sketched the kite shown. He asked his students to add a line segment such that it would divide the kite into two familiar figures. If Mr. Graham asked you to determine the area of the kite, would you rather use Molly's kite or James's kite? And give an explanation. So take a look at Molly's and James's kite, answer Mr. Graham's question, and then go ahead and answer number 2 and number 3 at the bottom of page 879. If I'm answering Mr. Graham's question, I know that everyone's answers are going to vary, but I would rather use Molly's kite because I would only have to calculate the area of one triangle since both of them in her kite are congruent. For number 2, a strategy that you could use was simply to find the area of the triangle using your formula 1/2 base times height. If you calculated the area, you could just then double it or take the sum of both of them in order to get the total area. If you are using Molly's kite to calculate the area of the kite, what additional information would you need? That's what they're asking you in number 3. The first thing you would need to know is the length of base AC, and I have that arrowed up at the top in Molly's kite. You would need to know the distance from point B to point D, marked in red. Or finally, you would need to know the distance from point B to line segment AC, that is marked in red. If you turn to the top of the next page, page 880, number 4 asks, if you are using James's kite to calculate the area of the kite, what additional information would you need? I'm going to leave the previous page on the screen so I can mark off the things like I did for number 3. So the first thing that you would need to know is the length of base BD, arrowed here in James's kite. You would need to know the distance from point A to line segment BD, marked off with the red line there. And finally, you would have to know the distance from point C to line segment BD. If we take a look at number 5, it says, how would the area of Molly's kite compare to the area of James's kite? I think that we know that the area would be the same because it is the same kite. They're both congruent. In number 6, now you are given measurements for each of the line segments in that kite. What they want you to do is calculate the area of kite ABCD using both Molly and James's strategy. So go ahead and do that to finish off problem 2. Here is what Molly's answer would look like if I use the formula to find the area of one of the triangles in Molly's kite. A equals 1/2 times 5 times 1.25. The area for the triangle then would be 3.125. If we double that, we get 6.25 square centimeters for kite ABCD in Molly's method. For James's strategy now, since both of his triangles were not congruent, we have to find the area for both of them and then add them together. So for triangle ABD, 1/2 times the base times height, 2.5 times 1.1 is going to give you 1.375 square centimeters. And for triangle CBD, we have 1/2 times the quantity of 2.5 times 3.9, which gives us 4.875. If we add those two together, we get 6.25 square centimeters for James's answer. Again, the same answer that you should have come up with for Molly. What I would like you to do for homework in 13.5 is problem 3, again dealing with composite figures. It ends on page 882. So finish problem 3 for homework. Please let me know if you have any questions regarding finding the area for a kite and for a rhombus. We are pretty much building off of our prior knowledge for the formulas that we've already used finding the area of triangles and of parallelograms. Let me know if you have any questions. Thanks.